Hello, this is Mr. Ferreira, and this is another one of my videos on research methods, specifically looking at the inferential tests that are correlation, and that's the Spearman's rank correlation and Pearson's correlation. Each test will have at least some reasons why we would choose it, and we see that we choose Spearman's rank correlation, or the symbol rho for rank correlation, if we are testing a correlation and the data is at least, or the variables are at least ordinal, or the level of measurement is at least ordinal. Now we go back to our flow diagram and we see that we've answered no to this particular question about nominal data, and we've answered yes to correlation. Okay, remember we're looking for the word relationship. And if it is, we're choosing the Spearman's rho test. The second part of that, as I said, the level of measurement is at least ordinal. So it can't be nominal data because it's not category data. And the reason I'm not saying anything about it being interval is that we haven't used some kind of measurement in order to have a look at this. So let's look at a hypothesis that could be a correlation. Participants' recall on a memory test is positively correlated to the GCSE exam performance. So we see here, we have a couple of things. We use the word correlation in our hypothesis. And we have two things that we could potentially have looking at in terms of covariables. It's a recall on a memory test and the GCSE exam performance. And we also know that it says positively correlational. So therefore, this hypothesis is directional. Now, when we do inferential statistics, we're trying to either prove or disprove a hypothesis. And we like to actually use a phrase called or reject a hypothesis. Remember the topic of falsifiability. So if something is significant, I want to be able to reject something. If something is insignificant, it's quite simple. I can reject the hypothesis because I haven't found a relationship between the two. So what can I reject if it is significant? Well, I can reject the null hypothesis. Now, this is just the situation where you're basically saying it's an empty hypothesis. Some people call this H0, H for hypothesis, 0 for the null, where I say there's no correlation. So therefore, if it is significant, then I can say I can reject the null hypothesis that there's no correlation between recall and memory tests and GCSE performance. Now actually think about it. Maybe there is something to this particular study. All the examples that I'll use will be actual studies that have happened. Are people who are good at memorizing things are the ones who do well in the GCSE exams? Now, what I can't tell you is exactly how they collected their data. But what we do have is we have two scores. Now, of course, think about the exam. Think about the different things that you might be asked to do. Now, this definitely looks like repeated measures. Score 1 and score 1, score A and score B. So don't jump to conclusions about design, because with a correlation, for example, I need to have covariables. And so therefore, the table of data may look like it's repeated measures, but it's not, because in the hypothesis, I've used the actual word correlation. So therefore, it has to be a correlation. And what we see here is that 10 participants took part in this particular score. So I'm going to say N is 10. Number, or N, is often number of participants. Oopsie daisy. There we go. So from this table of data, we've got a hypothesis that we saw in the previous page, we've got a null hypothesis, and we can start kind of looking at what we need to do. Now what happens is the calculated value is something which we do not need to do. This is done for you in the exam. But what I am going to introduce is another phrase called the observed value. Okay, even that I'm kind of observed value. Because depending on which textbook you look at, they might use the phrase calculated value or observed value. And I want you to see that it's the same thing. This is the value that came from your value, the value that you used in terms of collecting data. It comes from this table here. They've used some kind of formula to work it out. And what we find is that it says the calculated row is 0.56. 5658. Okay, so we now have an observed value or calculated value of 0.58. Then it says we need to choose our significance. So we need to decide what level I'm going to choose. And I've already repeatedly said to you, we choose 5%. This means the probability of making a type 1 error is 5%. Step 3, critical value. Hopefully from the scientist video, you've kind of seen how this works. We can't work out a critical value unless we know the direction, the number of participants, and the level of significance. So we know that n is equal to 10. We know that the significance was 5%, and we see that there is a one-tailed test because it was directional. With those three things in mind, when we look at the critical value table, we'll see that there's only one value of 0.564 that matches all three. One tail, 5%, and n equals 10. So we can then say the critical value is 0.564. But remember what I said during the sign test. We can only say that because we are able to state that n equals 10, it was 5% significance and one tail. Now, of course, most tables that we see may not just have a single value in it. It could be for both directional and non-directional and at different percentages. So please be careful that you read whatever the table says. Because each table also will have their statement of intent. So we see here the observed value of rho must be equal to or greater than the critical value in this table for significance to be shown. And another reason why I've interchanged the phrase of calculated value with observed value, because it will depend on who set the test. And this particular table uses the phrase observed. So therefore, we need to ask ourselves, does our value of 0.58 match this criteria or not? So let's write it out. The observed value is greater than the critical value. Therefore, the data is significant. Excellent. Therefore, we can do something with this. We can reject the null hypothesis. The table in the exam could display more than one level of significance. Please make sure you choose the correct table. So this is the example of that. There's the one-tailed and the two-tailed, and we see different values here. We also find that they don't want to waste paper, so they won't give you all of the table. We also see that they've used calculated rather than observed. So for you, you need to kind of make a mental note that observed and calculated mean the same thing, and that directional and one-tailed mean the same thing, and non-directional and two-tailed mean the same thing. Now, I know for the mathematicians out there, you might be screaming at me saying that's completely wrong, but my job is to help to simplify things. Now, you might have wondered about my previous hypothesis that said that there's a positive correlation between exam results and recall in a memory test. But what happens, for example, if when they worked it out, they actually worked out my rho value to be a minus 0.58? Because if any of you have done a correlation by hand, you would have seen that you can enter in the data and you can actually get a negative correlation. Now, of course, part of me would say, oh, we need to remember my hypothesis said that there would be a positive correlation. So therefore, if they have an answer that is negative, I can reject the hypothesis straight away. But that is something which is kind of often seen as a more complicated case. So please look out for tricks like that. If we ever do have a negative observed value or calculated value, what we do is we ignore the negative sign when we go to our table. We need to make sure that we can compare like with like. So if all the values in the critical table are positive, then we need to compare it with a positive sign. So in other words, we take the negative away. So then we'd say the observed value is greater than the critical value. However, we would reject it because the value was negative. So it's kind of a weird situation. It's pretty much that the data is significant, but the hypothesis itself potentially was flawed. So it could be that I need to restate my hypothesis and test again. Remember the whole test, retest, how we come up with a theory, either inductive or deductive method, that we need to go back to the drawing board and do it again. Now, of course, this is just referring to that particular situation, rejecting the original hypothesis because there's no correlation between recall and tests, recall and GCSE performance. So please kind of get your head around these types of ideas. Remember, I'm going to be explaining this in lessons as well. You should just have a look at it because you might find that actually it's as simple as this. These are examples. So you have n equals 10, directional rho equals 0.54. Your job is to go to the table of data and decide whether it's significant or not. Okay, so go through that, try it, and pause the video and see if you can come up with the correct values, whether you should reject or accept it based on this. Now what I've done is obviously I've kept your n values constant. I've also kept all your rows as being positive, but of course I've interchanged directional and two-tailed and one directional there. Now of course what you need to do is practice whether it's significant or insignificant. Okay. Now of course I've been talking about several things. I just want you to think about what you do before you reject the null hypothesis. You don't want to make a type 1 error. Okay, so make sure that your conclusion makes sense. So for example, if the calculated value ends up being negative and you've said that there's a positive correlation, you need to think about that. Now, for those of you who like to get a bit of practice, on the shared drive, I have a whole bunch of PSY A4 papers, and this is the paper that had research methods and a dictionary in it. And you can go to those questions and you can find questions that are research methods related, and all the correlation ones are there. Okay, and you can see that they really do like correlation in terms of the exam, so it's worth you practicing them. Now that is your Spearman's row. For the new specification, they introduced Pearson's. Now, I don't want to get too pent up about the different types of correlations. I want you to understand the point of looking for correlation. The phrasing of the words will be exactly the same. So in other words, we found the word relationship or correlation in terms of hypothesis. But this time I've added that the data or the level of measurement is interval. So put in kind of slightly different ways, this will be a hypothesis or an aim where we look at them collecting data that they've used some kind of machine, like a stopwatch or some kind of scale. I'll also say that there's parametric tests. Now, parametric tests are something which we usually decide on whether it's using some kind of nominal data. So in other words, go back to your levels of distribution, not nominal, normal data, levels of distribution. And I don't want to make it overly complicated, but we see that there is a difference between parametric and non-parametric. So if your measurement scale is nominal or ordinal, it's non-parametric. So in other words, when we've looked at your chi-squared or looked at something like your Spearmans, it's kind of relatively small amount of data. I had 10 participants there. But what happens if I was testing kind of a population? Then I'd go to parametric tests, and I expect of a population to have some kind of normal distribution. And if that is the case, then you're going to find that the Spearman's row perhaps is just a little bit awkward or not powerful enough to use. And so for that case, I'd turn and use Pearson's. So it's the same idea, because remember, I'm not going to be doing the mathematics, neither of you. Somebody else is going to be doing it. But of course, I need to choose which test to use. And so I'm going to use Pearson's. So parametric stats looked at a distribution that is normal. That's kind of what I repeated. So let's have a look at a situation in which this could be the case. So very simple hypothesis says there is a positive correlation between the number of days participants have been using biofeedback and the reduction of their resting heart rate. And what we find is that number of days is time, so therefore it's measured according to interval data. And of course, the resting heart rate is beats per minute. Once again, it's a machine that measures that. So of course, let's have a look and see what we could find. So we do exactly the same thing as we would for Spearman's. We state our reasons for using it. We change our reasons because of how we have done that. But the main difference is that we've had different types of data. So the actual critical value table looked quite similar. Let's give you an example of something that was perhaps a little bit more complicated. Okay, so it might look a bit like this. It might have more data in it, but ultimately it will still have exactly the same thing. We look at the number of participants, one or two-tailed, at what percentage, and we can choose one critical value. And then we follow the statement at the end. So why do we have two tests? Well, literally, because, as I said, one suits one type of study and another suits another type of study. So there we have correlation. The first test, perhaps I haven't done a fantastic job here, but I'm hoping that in combination of kind of going through the textbook and looking through your workbook, that this will make perfect sense. That's all for now. Okay, bye.